Hello, ladies and gentlemen. So today we're going to look at motion in two dimension, which is in particular projectile motion. So we're going to go right into the lesson right now. So what I've opened right here is some notes I made for you on projectile motion. So as you can see here, we have an object which is projected from the horizontal at an angle alpha with a speed of u. So as you can see, this letter here is u. So this object is projected from an angle alpha to the horizontal with a speed u. And this particle, of course, is this point particle here. As you can see, this vector pointing to the right is just the velocity of this particle, and it's a tangent to the curve, as you can see. This is tangent to the curve going there as velocity v, and going backwards there, tangent to the curve, is the drag force d. So this drag force is the resisting force to the motion. It's just the drag force resisting motion of this object. And the other force acting on this particle as it is moving freely into dimension is mg k hat. This minus mg k hat is just showing that gravity is always pointing downwards. This is why the minus is appearing here, because in most cases motion assumes that we take up as positive. So up is taken positive, down is taken negative. That's why you see this negative here appearing on mg. Since we know that to get the force of gravity, we must multiply the mass of the object times the gravity. Now this negative is appearing because of the fact that we've chosen up as positive. We take up as positive, but we know that gravity always points downwards. That's why it is having a negative here. So this is our xz axis. So yeah, we're using this as the x, and this we've made as the z axis. Okay, and let's see something here. So we're saying that a body that moves freely under uniform gravity and possibly air resistance is called a projectile. Any body that moves freely under uniform gravity can be called a projectile. And projectile motion is applied in ball games such as golf, etc. People playing golf, they always apply projectile motion. And people playing basketball, when they are throwing the ball in the net, that is a projectile. The path taken by that particle or the ball will be called a projectile. Okay. So this is basically the same thing which you did in first year. So here we're saying that with initial conditions v, okay, as you can see, this is v, vector v is equal to u cos alpha I plus u sine alpha k hat. So this is the x component of velocity, as you can see. U cos alpha is the x component of velocity. That is something which you can remember from first year. Let's just go back here. Okay, so when you look at this u, this speed u, the initial velocity, of course, u, when you look at when you look at the component it makes with the x-axis, we find that it is u cos alpha. Because if you set up a triangle here, if you make a triangle here, you find that this x component here will just have u cos alpha, and the vertical component will be u sine alpha. Okay, that's why we have this part here called u cos alpha. Okay, this is why we have this u cos alpha here plus u sine alpha. This is the y component of velocity. Okay, this is the rather the z component of velocity. So we're not using y, we're using the z. So we have the x and z. So we have this is the x component of velocity and this is the z component of velocity. That is when t equals 0. These are the initial conditions. The initial conditions always open at t equals 0. So if we now write v is equal to vxi plus v subscript zk, so as you can see here, we have this u cos alpha, which is written v subscript x, and u sin alpha, which is written v subscript z, and take components of these equations in the I and k directions. We obtain the two scalar equations of motions, dv subscript x over dt equals 0. So what is dv over dx? This dv over dx is just acceleration in the x direction, the x component of acceleration. So we've taken this x component of acceleration, v subscript x. So it's just in the dvx over dt, which is acceleration, which you know. Okay, dv over dx just used to calculate acceleration. But since we have subscript x, mean that we're calculating for acceleration in the x-axis, which is 0. And this is something we know. We always know that the x component of acceleration is always 0 for any projectile motion. It's always 0 for every projectile. So this is always a fact. It is always 0. And dv z over dt is equal to minus g. Okay, dv z over dt is equal to minus g. Why are we saying this? We're saying that this is the z component now, right? Which is the vertical component. Here z is the vertical component. So we're saying dv z over dt is equal to minus g. Okay, and mind you, here on this part, instead of using z, we would have used y. Okay, so yeah, so it's just that in the notes z was used, but if we want, we can use y here. It won't make any difference. Otherwise, it's just about understanding what is going on. So dv z over dt is just the z component of acceleration, or the vertical component of acceleration. This is the vertical component of acceleration, and we know that in the vertical plane, the only acceleration which acts on it is gravity, which is g here. We know that gravity acts in the vertical plane. That's the only component of acceleration which acts on the vertical vertical axis. And the minus here is appearing because we choose up as positive and down negative. Now, since gravity was acts down, that's why there is a negative here. Since up is positive, down is negative. So now one thing we know is that gravity always points downwards. That's why there is a minus here. Okay. So I was saying that with respective initial conditions, v subscript x equals u cos alpha and v subscript z equals u sin alpha when t is 0. Simple integration then gives the components of particle velocity to be v subscript x equals u cos alpha and v subscript z is equal to u sin alpha minus gt. Just integration of this and this, you get that. Okay, with the respective initial conditions, v subscript x equals u cos alpha and v subscript z equals u sin alpha at t equals 0. We're going to get this part and this part. Okay, so that is just when you integrate this by using this initial condition, you get this. You integrate this by using this initial condition, you get this as an expression. So what are we saying? The position of the particle at time t can now be found by integrating the expressions for v subscript x, v subscript z, and applying the initial conditions x equals 0 and z equals 0. Okay, that is when t equals 0. And when you do this, you get x equals u cos alpha t, comma z equals u sin alpha t minus half gt squared. Okay, so this is what you get by integrating the expressions for v subscript x and v subscript z. Okay, we can find the position of each of them. Okay, so these are equations which you have seen before, of course. You've seen the equations of uniform motion, which are just these. And of course, there's this example B here, which is saying show that the path taken by the particle is an inverted parabola. So when we look at this part, which is telling us to show that the path taken by the particle is an inverted parabola, when you look at the answer, we're just saying that to find the path, just eliminate t from the trajectory equation. So it's simple elimination of t from the trajectory equation. So we know the equations are here. We have this equation and this equation. Okay, so when you make t the subject to the formula from this equation here, this one here, you make t the subject to the formula and you put that t in this other equation, you're going to get this expression here. And simplifying this expression further, you get this expression, which is z equals tan alpha x minus this whole expression that side. And when you look at this, you find that this is an inverted parabola. This is an inverted parabola because when you look at this equation, what do you notice? You notice that this is just a quadratic equation. Okay, this is a quadratic equation in the variable x, right? So as you can see, this is x squared, then you have x. So this equation is quadratic. These parts in brackets, they are constant. Even this part is constant. So that's why I was saying that this is a parabola. And looking at time of flight and range, of course, just like something you did in first year, I'll just go through it quickly. So finding the time of flight and the range of the projectile on a level ground. Time of flight is just the time taken to complete the projectile, to complete the motion until the particle falls to the ground. So that's the time taken, that is the time of flight. So here we're saying find the time of flight and the range. Of course, the range is just the horizontal distance for a projectile. So on the level ground, the motion will terminate when z is 0. Okay, on a level ground, of course, the motion will only terminate when z is 0. That is the z component of displacement is 0. Okay, why is it 0? Because the object will come back to its starting point. It will come back to its starting position in terms of displacement. So if you throw a stone up, the moment it hits back the ground, the y component of displacement will become 0. That's just how it is, and that's how it is because you get back to the same point. Okay, since we're talking about displacement. Now from the second trajectory equation, this happens when u sin alpha t minus half gt squared is equal to 0. Okay, so you see, since we said z is 0, we'll make this expression to be 0. Hence the time of flight, tau is given by tau equals 2u sine alpha over g. Oh, this is just what you get simply by making t the subject of the formula. That's what you get. And then we can say, of course, here, when you make t the subject of the formula here, you will get this equation. Of course, you also have another equation where you have t is equal to 0 and this other t. So this is the symbol of use for time. This is just tau. This is just tau. Don't be confused by it. This is just tau. And the horizontal range r is obtained by putting t equals tau, of course. So that is what you get as the time of flight. So now using this time of flight, we can get the range r, which is the horizontal position of a projectile. That is the range. And the range, of course, can be placed in this equation here using time of flight. So you must use the time of flight and replace it here because you want the horizontal uh, component of displacement, so which is the range, of course. So you must put the time of flight here in this equation, but substituting for t. That's how you get. When you do that, you have to get this expression here as your answer. You have to get u squared sine 2 alpha over g. And for the maximum range, so max range alpha, we are saying that find the value of alpha that gives the maximum range on level ground when u is fixed. So, well, the maximum range is just the maximum range you can get when a projectile is launched. That's just the maximum range, which is the horizontal position, the maximum horizontal position you can get when, of course, alpha is fixed, the angle is fixed. So now here, something we should know is that r is maximum when sine 2 alpha is equal to 1. R is maximum when sine 2 alpha is 1. Okay, why are we saying this? Because the maximum value that sine 2 alpha can have is 1. That's the maximum it can ever have. And when you solve for 2 alpha, you find that you solve for 2 alpha, or you maybe, let me say, when you solve for alpha in this equation here, you find that alpha will just be pi over 4, which is 45 degrees. Okay, alpha will just be pi over 4. And when you substitute for alpha in this expression here, you find that the result you get is r max equals u squared over g. Because sine 2 alpha, this will turn out to become 1, to just be 1. This is just 1. Hence, if sine 2 alpha is 1, you get u squared over g as the range. Well, you shouldn't be confused because this alpha is just pi over 4, which is 45 degrees. Here, what we're simply trying to say is that when you launch a projectile at an angle of 45 degrees, okay, when you launch it at an angle of 45 degrees, that's the only way you get a maximum range. That's the only way you get a maximum range, which is the horizontal position or the horizontal displacement made by a projectile. Alright, for now we'll end here. Then in the next part we'll look at questions on projectile motion. Alright, have a good day and see you in the next video. Thank you.